Okay, good afternoon. Let us start our lecture. Before that, just to remind you, we have the midterm test on Saturday, week 7. I think it's 5th of October. So it's in the morning from 10 to 11. So you should be in the venue 15 minutes before the start of the test. And the venue is the multipurpose sports hall. I believe it's hall 1. All right. Is it a closed book test? You don't know, right? Okay. It's a closed book test, but with one help sheet, A4 size help sheet. Am I right? Huh? Did you able to access to the announcement of the lecture group 1? No? Oh, okay. Yes, it's one help sheet, A4 size. If I remember correctly, let me check. I will announce it again. All right. Okay. Last week we talked about distribution of a random variable. So there are two types of random variables. One is discrete and one is continuous. So the way to distinguish these two types of random variable is look at the range or the possible x values. If the x values are over a certain interval, all right, no matter whether it is from minus infinity to infinity or just over a very small interval, all right, then it's continuous. Otherwise, it's considered as discrete. So discrete usually means that it's not continuous. So it's some gaps, all right, between the values. So usually the discrete random variable takes the value of integer values or even include negative numbers. But basically, most likely they are integers, all right. But it's not just limited to integers so long as there are gaps between values. Then it's considered as discrete random variables. So the way to do things is slightly different for these two types. For discrete, we use summation to handle the probabilities or to add the probabilities for different values. While for continuous, we use integration. We also talk about another type of way to represent a random variable. It's called cumulative distribution function, the capital F. All right. So here we continue with the examples. So here, example 4. So we are given a random variable, x, all right? And the range of x is between 0 and 1. For within this range, then we have a values associated to each value. And this number, these values, represent the uncertainty or the degree of uncertainty or how likely that the random variable takes that particular value. So long as it is between 0 and 1, then it's equal to 2x. All right. So in other words, when x equal to 0.5, then the f of x equal to 1. When x equal to 3/4, then the f of x equal to 1.5. 1.5 is bigger than 1. How come it can be bigger than 1? All right. So remember, for continuous random variable, the value f of x here is not the probability. This is not the probability. But instead, it is called probability density function. All right. So what does that mean? Let me just repeat it again. So basically, f of x, all right, you can think of it like this. So this is f of x. This part is f of x, the density function. So it basically tells you that it's the chance that x falls within the interval x plus delta x. So this is of width delta x. So f of x, the density times the width will give you the probability of x between x and x plus delta x. All right, so this is the probability that x falls within that small interval, x to x plus delta x. All right, so in other words, if you divide this by delta x, then it becomes the density. Remember in physics, there's this well-known density. So what is the definition of density? In physics, mass divided by the volume, right? So it's the same thing. So instead of volume, we just have the width. So these density functions, all right, divide by the, multiply by the width, will tell you the chance or the probability that x falls within this interval. So that's why it's called density function. So f of x, the little f of x, is not a probability, but it's the density of the probability in the neighborhood of x. A very small neighborhood. You can think of it, delta x is very small. All right? So now, in this example, the PDF, probability density function, is equal to 2x, when x is between 0 and 1, and it's equal to 0 otherwise. So we are asked to find the cumulative distribution function. We are asked to find this, which means probability of x less or equal to x. All right? You have to understand this notation. So it's the probability of the random variable. The big capital letter X represents the random variable. It's a variable. And associated with it, there's a probability density associated with it. And less or equal to a constant. This little x is a constant. It's an argument. It's fixed. All right? Okay. So we are asked to find this one. So you can think of it like this. In fact, this is 0, 1. So this is the f of x, like that. All right? What is this area? What is this area? Remember the definition of a PDF? Integrate from minus infinity up to infinity. That means the area under this function, f of x. This f of x has 3 parts. From minus infinity to 0, it is 0. Then from 0 to 1, we have this line, straight line. All right? And then from 1 onwards, again, it is 0. All right? So basically, it's the area under this curve. Should be 1. So you don't have to do integration. The answer is 1. Under the area of this triangle is 1. All right? So what is f of x? A capital F of x. Capital F of x, all right, depends on where your x is. If x is here, then what is f of x? 0. Because there's no probability. You try to collect your density from minus infinity up to this point. There's nothing. 0. So you get a lot of zeros. So it's still no density. All right? But the story is different when x is between 0 and 1. Then you'll be from minus infinity up to this point, then plus this part. All right? Okay? So how about x is here? Then you go from minus infinity up to this point. All right? On the way, you collect all the density. So up to this point, the density is 0. Then you collect all this density, which should be 1. And then after that, no more additional density. So the answer is 1. Okay? So here it is. So this is from the definition. All right? Basically, you accumulate all the densities from minus infinity to x of f of t dt. So now I change these arguments. I don't want to use x. And I told you that I don't use x because I don't want this x. If I use f of x dx, then this x and this x are 2 different things. All right? The f of x, the x is the argument for the integration. While this limit x is a fixed point. It is the one that I refer to. It's here. This x has nothing to do with this 2x. This x only refers to the limit, upper limit. All right. So now, in order to avoid the confusion, I replace the f of x dx by ft dt, or any other letters that you want. All right. So we start the integration. So I have to separate into 3 regions: less than 0, between 1 and 0, and bigger than 1. All right? So this is how we do the integration. Why I have to do it in 2 parts? Because the f of t takes different form over this region. From minus, when this part referring to t is between minus infinity up to 0. This part referring to the t between 0 and x. All right? And these are the f of t. This is also f of t, but only valid for this. This f of t equal to 2t only valid for this. All right? So that's how you do it. So the last one is from minus infinity to 0, then 0 to 1, and then 1 to x. All right, so after you complete the integration, so these are the answers. Now, I have to stress that the CDF, the capital F of x, should be, you should have this capital F of x for all x in the real line. So in other words, you should be able to tell me if x equal to minus 1, what is the cumulative density distribution function? All right? And if x equal to 0.5, what is the cumulative distribution function? If x equal to 100, what is the cumulative distribution function for this given density function? So it's true for all x. But of course, the form may be different. As you can see that from minus infinity up to 0, the CDF is equal to 0. No cumulative density. But then between 0 and 1, then it depends on the magnitude x. So it's x squared. But once you go beyond 1, x takes the value bigger than 1, then you are already collect all the density that are available. So it's 1. All right. So if you draw, so we have a picture for this one, a graph for this one. So it's 0 and then 1. So it will be something like this. This is not. In fact, this should be y equal x squared, or f of x equal to x squared. All right, over this region, and then this part will be 1. So it's like that. Okay, so this is y equal x squared. This part is 1. So, all right, so this is 1. So a non-decreasing function, remember it's non-decreasing function. That means it's keep increase or at least stay as those are less than it. All right, so this one not increase, not decreasing. This one not decreasing, and this one is increasing. So this is the graph for the CDF for this particular given PDF. Now, so continuous random variables may be easier, but remember, for discrete case, last week we talked about it. So for example, for discrete case, this is the probability function. For example, like this. All right? So the probability function takes the value, let's say 0, 1, 2, 3, 4, 5. So it takes probability only when x equal to 1, when x equal to 2, when x equal to 3, x equal to 4, and x equal to 5, for example. All right? But then what will the CDF, the capital F of x, look like? So the capital F of x, all right, so f 1.5 is 0. There are no probability at this point. But this one is not. This one is not 0. Why? Although the probability at that point is 0, but it's cumulative. That means it tries to collect all the probability for those x value which is less or equal to 1.5. So in other words, the CDF will be go like this. Up to 1, then jump, all right, of this height. Then once it reaches 2, it also have another jump. So it's a step function, which means that for any x value, I can tell you what is f of x. And they are not necessarily 0. Remember, it's cumulative. So long as any x value less than it has a probability, then it belongs to the cumulative at that distribution at that point. All right? So make sure that you understand this one. Otherwise, you think, oh, capital F 1.5 of this graph is 0. No, it's wrong, because F1, the little F1 has a probability. So that will be included as part of the capital F 1.5. Okay. So here x represents the stress in terms of PSI. So it's given by these functions. Okay, it looks very complicated, but you can think of it like this. This one and this one, theta square, so complicated. I just call it A. Call it A. It's just a constant. Call it A. Then it looks easier. To a simpler, a form which is simpler, 2A. Okay, so that is, all right, so maybe easier to see it. All right, so when x is positive, the PDF take that form. When it is negative, it's 0. All right. So, and we know that it's continuous. Why? Because x takes any values between 0 and infinity. No gaps. All right? So verify that f of x is legitimate PDF. So remember, in order to be a well-defined PDF, it needs two things. What are these two criteria? The first is that this f of x must be greater or equal to 0. And secondly, integrate from minus infinity to infinity, f of x dx has to be 1. All right, you need these two criteria. By the way, I write down f of x semicolon theta. Okay, this is just to tell you that we are talking about a PDF. Now, PDF is referring to the random variable x. But the PDF may also depend on some other quantities. So in this example, the other quantity is theta. Or if you like, you call it A, which is theta square. In fact, it depends on theta full theta square. So there are two parts of this function. It is x, and also there's a theta. All right? X is the key one. It is the value of the random variable. While theta is just a constant to illustrate maybe there's different PDF. You can have different theta values and you have a different PDF. All right, but it's still within that form. So theta, we call it parameters. That means it's a constant. This constant is identify or indices or characterize the distribution in that form with that particular theta. While x is the value of the random variable. All right, so is this positive? Is this positive? So you have to know two things. All right, maybe. Basically, e to the power any number. This is always positive, even if b is a negative number, right? So let's say e to the power minus 5. And this is not a negative number. This one means that it's 1 over e to the power 5. All right? E is just a constant, a positive constant. You raise it to power 5. It's still a positive number. So take the reciprocal, it's still a positive number. So e to power anything, either positive or negative, is bigger or equal to 0. In fact, it's bigger than 0. How about if b equal to 0? Is the whole thing equal to 0? Is it 0? Is it 0? No, right? Use a calculator, you type exponential to power 1 is 2.7 something. Not 0, right? Okay. Multiply them. So it's e to the power 1 times e to the power minus 1. So it should be e to the power 0. So it's equal to 1. Any number raised to the power 0 is 1. Remember that. E to the power 0 or a to the power 0 is not 0. Okay? So therefore, what I'm trying to say is that this part is always bigger or equal to 0. Bigger than 0, in fact. Then this part is also bigger than 0. Bigger, because x is bigger than 0. Now, so now you can see that why we write it as theta square. Right? If I don't write it as theta square, because theta square, it does not matter whether your theta is positive or negative. Theta square is always positive. So at least it satisfies the first criteria. The PDF is bigger or equal to 0 for any x. How about this one? This one does not guarantee that this is bigger than 0. In order to make sure that it's bigger than 0, I need to specify that, which is given, x bigger than 0. Not only that, I also required a bigger than 0. A bigger than 0. All right? So this seems to be not very important, but it's very important in the sense that you have to understand what each one have their role to play. We make sure that this is a PDF, so therefore it must be bigger or equal to 0. The next part is the second criteria, integrate from minus infinity to infinity, that is equal to 1. Then in particular, if theta equal to 100, find the probability of x at most 200. So you are asked to find probability of x at most 200. You cannot exceed 200, right? And then less than 200. All right. At most 200, right? Less than 200. Is it correct? Huh? Is that what we are asked to find? Huh? Okay. And then at least 200. So a bit confused. Okay. Also, we'll generate the expression of x less, probability of x less or equal to lead to x. This is nothing but just our CDF, our cumulative distribution function. Let me ask you, this one, you'll get the expression. So this expression is a function. Inside this expression, what will you see? Will you see x is likely? All right? You also should see theta. Why theta? Because theta comes with it. You cannot get rid of the theta. The probability density function with the theta. Remember the lead to f of x, there's a theta there, theta square in fact. All right, so we expect this to be a function of x and theta. All right, so obvious. Although I say obvious here, but you have to really, really understand that. Why is it obvious? All right, because e to the power something is always positive, and the x is in the range of positive, and finally with the theta square, which is also positive. Then you have to integrate. All right. So I substitute this. Remember there are two forms for this PDF. One is 0. When is it 0? It's whenever it's between minus infinity to 0. The PDF is 0. All right? Then it's from 0 to infinity. So the PDF is of this form. All right? And dx. So this part since the integrand is 0, so when you integrate it's 0. So I delete it. All right. So I want you to understand, or at least, why is it equal? How come this one suddenly becomes 0? There's reason behind. Because when I do the integration, I partition into two parts. Why I partition in two parts? Because there are two forms of the PDF. One is 0. The other is x over 2 theta squared times e to the power minus x square over 2 theta squared. All right? So this part get rid of, so it's just remaining with one integration. Ooh. Wow. All right, this one basically is a sort of integration by parts. Okay, think of it. If you differentiate e to the power minus x squared over 2 theta square, what will you get with respect to x? Then you will get, applying what we call chain rule, so it will be e to the power minus x squared over 2 theta square, and then differentiate this part, gives you minus 2x 2 theta square. All right? Okay, there's a negative sign. All right? You differentiate ax with respect to x. This will give you a e to the power ax. All right, just apply. A is okay, slightly more. All right. Okay, so you see, this is exactly the same as this one. So in other words, this is equal to differentiate this one. So the answer is e to the power minus x squared over 2 theta squared. If you have problem in doing integration, do a revision on how to do the integration, especially with exponential functions, and also how to do integration by parts. Integration by parts. All right, substitute in, and you got the answer 1. All right. There's a negative here. All right? So substitute 0, it is minus 1. So it's minus 1. Is there a negative sign here? Infinity. So it is 0 and then minus 1. Minus the whole thing. So the answer is 1. All right? Okay. Then suppose theta equal to 100. So now I replace the theta equal to 100. So at least, at most 200. So integrate from minus infinity to 200, or just from 0 to 200. So it's equal to minus e to the power minus 2 plus e to the power 0. So the answer is 0.8647. All right. So how about at least 200 and not more, less than 200 and at least 200. For continuous, they are the same. All right. The first one is less than 200, x less than 200. The second expression is at least, at most 200, all right? So it's the same. We don't have to redo it again. Then this is at least 200, so it's greater or equal to 200. Now this is, straight speaking, this is not correct. All right, it should be 1 minus probability of x less than 200. All right, you see, sometimes it's too lazy to write so many steps, but you must understand why you can do it this way. Straight speaking, this equal to 1 minus this one, because this is the complement event of this. But because x is continuous random variable, this event and this event, these two events, all right, are not the same. One is less than 200. The other is less or equal to 200. So they are not the same. But the probability of these two events are the same. Why? Because the probability of x equal to 200 for continuous random variable basically is 0. So it doesn't matter. These two events have the same probability. All right? So let me recall the example that I told you last week. Toss a die. What's the chance getting 1, 2, 3, 4, 5, 6? All right? Or what's the chance getting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Now the two events are different. One is 1 to 6. The other is 1 to 10. So the two events are different. But the probability are the same. All right? Because the chance getting 7, 8, 9, 10 for toss a die is 0. So in that case, the probability of these two events are the same. But does not mean that these two sets are the same. So the same applied here. For continuous, it doesn't matter. This x less than 200 and x less or equal to 200 are the same. But when you come to discrete case, this distinction is very important. All right? Okay. So for x bigger than 0, I just continue to do it. So this time, I don't write x. Instead, I write it t. So I just integrate it. So the answer is 1 minus e to the power minus x squared over 2 theta squared. So that is the CDF. The CDF of x. All right? You see, this basically is the same as before, except that I don't have a number here. In the A and B, or A part, this is 200. So now I just replace it by x. In order not to confuse us, so we start right from the beginning, it's f of t instead of f of x. All right, so this is the answer. And, don't forget, this equal to this. Is not true for all x. Not true for all x. So when is this a valid expression for the CDF? It's only when x bigger than 0. If x is less than 0, it does not equal to this one. Why? What happened to those x such that x is less than 0? I say it does not equal to this one. Why? Because in that case, you integrate from minus infinity to x. What can you say about this one? If that means that the t, because t is from minus infinity to x, where x is less than 0. So all this t must be less than, you remember, t is, I'm talking about integrate this one. So we are talking about t between minus infinity to x, and x is less than 0. So in other words, t is also less than 0. So what can you say about f of t when t is less than 0? It's 0. So therefore, this part is wrong. You cannot write this as this one. So that's why this is not the answer for x less than 0. All right? So it's important that, all right, you got the answer, but the answer is only valid for x bigger than 0. So in other words, you also have to specify what is the capital F of x, the CDF, when x is negative, which is 0. All right. So it's also stay there. All right, so now when I come to find out what is the chance that x falls between 100 and 200, then I just, this one, strictly speaking, is probability of x less than 200 minus probability of x less than 100. Right? So, but this one is the same as less than 200 minus probability x less or equal to 100. This is my F200 and this is my F100. So it's equal to this. And what is capital F? From part C we have already done it. So I just substitute, replace the x by 200, replace the x by 100, and then I get the answer. So the answer is 0.4712. All right? Of course, if you think that you have a lot of time and you don't mind to do the integration again, another way to do it is to integrate from 100 to 200 and the f of x dx. And this is what? X over theta square, which is 200 square. And then this is e to the power x square over 2 times 200, right? Sorry, theta is 100 square, so 100 square. All right, dx. Why bother to do it again? You have already done it in part A. You have done it in part C. Why bother? So you just apply the result of CDF, the formula that we obtained for the CDF. All right? I think I showed you, yeah, this is the alternative way, yes? Do the integration, right? You still get the same answer. And the worst scenario is that you may get the wrong answer because you make a careless mistake. So do the easy way, all right? Okay. Okay, so we spend a lot of effort or discussion on how to find a probability given the probability function lead to f of x or probability density function. All right. Then we also talk about the cumulative distribution function. So now we move to another way to understand about the behavior of the random variable or the distribution. We try to summarize a given distribution. So we want to use one number to summarize the distribution. So that is called expectation or expected value of the random variable or sort of mean. All right. Now, from now on, throw away your definition of mean, all right, which is you have a bunch number, right? And then you just add them up, right? Divide by n. This is the way that you learned about mean, maybe from primary school, secondary school, all right? But now, when we say mean, it refers to the expected value of the random variable. Or in other words, the variables take different values. Now let me ask you, if a variable takes only one value, then what do you expect the value of this variable? It must be the same value. It's a constant. All right? So in other words, okay, if I have x, it always takes the value 0. Then what is the expected value? 0, because it's always 0. But what happens if x equal to 0 and 1? What do you expect? What's the mean? So naturally you will think that 0 plus 1 divided by 2, so it's 0.5. All right? All right? Now, let me ask you, suppose I have a population with 10,000 individuals in this population. Only one guy got a 0, got a value 0. The rest got a value 1. So I ask you, what do you expect if I select 1 from this population, 10,000 of them. 9,999 of them have a value 1. Only one guy or one individual got a value 0. So what do you expect when you draw it? One individual from this population. 0.5? 0 plus 1 divided by 2 is 0.5. No, right? So most likely you will see a 1. All right? So that's why we will think that each of this value will associate with a probability. So in my example here, the 1, the value 1, this value, associate with a value, a probability. It is 9,999 over 10,000. And while 0, associate with it a probability which is 1 over 10,000, a small probability. All right? So what we expect is more closer to the 1, because 1 has a large probability to it. All right? So your 0 plus 1 divided by 2 basically is a very special case. You just think of it, half of the population are 1s, half of the population are 0s. So that's why you think that the mean is 0.5. All right. So from now on, we are looking at more complicated situations. The values in the random variable may take a different, associate with it different probability or probability density function, probability density. So therefore, it's not simply just add the value and then divide by the number of observations. This formula is not valid for infinite populations. All right. Here is the definition of the expect value of a random variable. Because the random variable basically represented by the distribution. The distribution tells us everything about the random variable. So now I want to have a number, a constant, that will tell me what do I expect about this. Or basically, to some extent, it is where the center of the distribution is. All right? So it is the value times the corresponding probability of these values. That means if it's a higher probability, then this value contributes more to the expected value. All right? So all possible value of x. All right, times f of x. This is only for discrete random variable. For continuous, then instead of doing summation, you see, summation xf of x, this is for discrete case. So now, for continuous case, I still have to multiply x times the probability density function, but no summation. Instead, we do the integration. All right, to do the integration from minus infinity to infinity. So you may consider the expected value basically is the weighted average. Each value is weighted by its density or weighted by its probability or proportion. All right? So the expected value exists provided that the sum or the integral exists. All right? Mathematicians like to make sure that everything is fine. So I give you a formula, but at least the formula should work. So your PDF, all right, or your probability function times x, and then you do the sum or do the integration, it exists. All right. Most of the distribution that you encounter so far or going to learn or discuss in this module, the expectation and the variance, later we'll cover what is variance, are all they exist. But there are some other distribution for which the mean does not exist. The mean does not exist. All right? So that's why it seems redundant now. I have to keep telling you that, okay, make sure that this one exists provided that the sum or integral. That means I can write this formula. But when I sum them up, all right, this becomes an infinity. So in that case, it does not equal to a number, a particular number. Then the mean does not exist, or the expected value does not exist. Okay? So, here I just give you an example. If f of x equal to 1 over n, all right, for each of the n values of x, so the mean is equal to the xi times the corresponding probability function, which is 1 over n. So it looks as if it is sum up all the value divided by n. All right? So this is what our usual definition of mean. So it's average of the n items. Okay, let's look at example. Ooh. Now here's an example. We have a game. I drop this game. So we will gain 5 if it gets all heads or all tails in tossing a fair coin 3 times. So that means toss a coin 3 times. So if you got this or got this, then we'll get $5. All right? And if it pay out 3 if either a 1 or 2. All right, so 1 head, right? This is 1 head, or 2 heads, or THH. So if any one of these, 1 head or 2 heads, he has to pay $3, pay out. Instead of gain, now you have to take out from your pocket 3. So what is his expected gain? What it means is that, or you can think of it like this. X is the amount that he gets. All right? So what are the possible values in this case? Can it be 0? X defined as the amount of money that he will get. All right? Related to the outcome of toss these 3 coins. Can X be 0? Think of it, when he will get 0. So you go back, look at your outcome. There are altogether only 8 possible outcomes. The sample space only have 8 possible sample points. All right? Do you have any outcome set related to $0? No. There are only 2 possible values. One is that he get, that means he gained $5 or 5 units. What's the other one? What's this 3? Does it mean that he get $3? Why minus? Why minus? Oh, okay, it says that it's a pays out. That means you have to pay $3 to the other parties, all right, when you have this outcome. So you read the question carefully. There's no free lunch. This outcome you got $5, that outcome you got $3. No matter what, you will get something. No, you have to pay something, all right, when this outcome, set of outcome come up. All right, so what's the expected gain? So if I toss 3 dice, I got head. I got $5. Well, what do I expected gain? Just like toss a coin. Before I toss it, it's either a head or tail. But once I toss it, it's a head. Then that's the outcome. So the same applied here. So what it means is that, okay, I have this 2 possible value. One is 5. The other is -3. So ask yourself, how likely I will get 5? So it's equivalent to getting 3 heads and 3 tails, which is 1/4. Am I right? 1x plus 1x. Then the chance of getting, so there are 2 values for x, either -3 or 5. So the probability of getting a 5 is 1/4. So the probability of getting -3 is 3/4. All right? How to get 1/4? Because there are 2 outcomes, head, and tail. that will give you $5 out of 8. So it's 1x. So now the expectation of x, so here it is. So the expectation will be the value 5 times the probability x times f of x, and sum them up. Because there are only 2 x values, so it's 5 times 1/4 plus minus 3 times 3/4. So it's minus 1. So what does that mean? It means that, all right, if you toss the 3 coins, either you got $5 or you have to lose $3. But I can consider this expectation is that when you do it many, many times, tossing these 3 coins many times, sometimes you got $5, sometimes you lose $3 as a whole. All right? In the long run, you expect that you lost $1 per game. All right? So, it's not a good, it's not in favor to you. All right? So, of course, the next question that we would like to ask is the following. Right now, this way of paying the gain and the lose seems that it's not in favor to the player. So I ask, what is how to divide the gain, the amount of gain and lose, so that this is a fair game. A fair game. So you see, I have a higher chance to lose. All right? And once I lose $3, 3 units. And I have smaller chance of gain or win, but that what I gain is only $5. So it's not good for me. So I ask whether to make it fair, which translate means that my expectation of payout should be 0. I don't gain from you, I don't lose from you in the long run. So that is a fair game. So you have to decide on, for example, I fix. Yes, you got 3 heads, 3 tails, you will get $5. So now I ask my question, how much should I lose if the others outcome show up? How much should I pay for it? Instead of $3, it should be smaller. Maybe 2.5, maybe 2. So you have to figure a number to make it a fair game. Okay, so we lose 1 per toast in the long run. This is important how you interpret it. That means you repeat this experiment many, many times. All right, then in the long run, you lose one unit per game. So now, if I ask you, what should be the money that you should pay out if it turns out to be other outcomes, 1 head or 2 heads? What's a reasonable one? So naturally, since -3 will lead you to lose $1, so don't pay so much. Check. How about -2? Will it make the expectation? That means I change. All right? Will this give me expectation equal to 0? All right? I want to adjust this number so that to make the expectation of x equal to 0. So it's fair to both parties. All right? So is this the answer? X equal to -2. All right? You work it out. If not, then you try other values. Or, better, don't use brute force. Don't plug in number and try to get the expectation whether it's 0 or not. Maybe for computer science, or use the program now, write a do loop and then check it out. But think of it, can we set up an equation and solve the equation and get the answer right away? That's how mathematicians think of how to find a solution. You see what I mean? My question is, what is this value to make expectation x equal to 0? Keeping 5 there, keeping the probability the same. 1/4 and 3/4, so what is this value? So one way is by brute force. So I'm smarter, I don't use calculator to do it, I ask the computer to do it, I write a program, do a do loop, okay, try try to replace that value by minus 2.5, minus 2.4, minus 2.3, and until I reach expectation x equal to 0. So that's one way to do it, fine. But for mathematician, we'll try to set up an equation with this variable, this as the variable. This part as the variable. An equation with that, all right, based on the expectation of x equal to 0. And then try to solve that equation and try to get the answer. All right? So here's the tips. In the exam, you don't have a computer to help you to run the program. You have a calculator. If you use brute force, then you have to try a few values to get the answer. But if you know how to set up the equation and solve a very simple equation, and you will get the answer right away. All right? So in other words, you better try this, solve this expectation of x equal to 0. Try to change this value, how much money you pay out, all right, in order to get the expectation x equal to 0. All right. Example 2. So roll a die, and you pay C to play the game, and you get I if the number I occurs. Roll a die. Die have 6 numbers. So if you got a 6, you got $6. If you got a 1, you got $1. So how much money you have to pay out in order to be fair? All right. So that means expectation of game equal to 0. All right? So, in this case, what is the random variable? Okay, there are many possible random variables here. One obviously is the outcome of the die. And what are the values? 1, 2, 3, 4, 5, 6. All right? And then the next question is, okay, these are the values. Then the next question is, what are the probabilities associated with this value? So assume it's a fair, a balance. I say balance, that means fair. So each value should have an equal chance of occurring. So it means that each one has 1/6 of chance of occurring. All right? Then, so this x is the outcome of the die. And then the probability is 1/6 for each one. All right? Okay? So now, I have to pay C dollars in order to pay the game. So if it turns out to be 1, then how much I gain? So, it will be 1, that's how much you gain, minus C. This is the amount of money that you gain. Am I right? You have to pay C dollars. At this point, I don't know what C is. I pay C dollars. But if the outcome is 1, then we'll get back 1 minus C. I will get back $1, but I already paid C dollars. So similarly, okay. So now, let me ask you, the gain. Can I express this gain, which take the value 1 minus 2, 1 minus C, 2 minus C, 3 minus C, and so on. So can I express this as a function of the random variable x, where x is the outcome of this die? So it's already there. So this is equal to the amount of money I get, which is equal to the outcome of the die, minus C. Right? Always, other people tell you this, it's so straightforward, so easy. But you have to think of it, what are the random variables? So this experiment is toss a die. So the outcome represented by x, which is 1, 2, 3, 4, 5, 6. All right? And you have to answer what are the corresponding probabilities. After that, then I link up, because I want to find the expectation, the expected gain. So I have to express this gain in terms of the outcome x. So it's x minus c. X minus c. So let me ask you, is gain a random variable? is gain a variable? Is that variable? Is always the gain equal to a particular value? No, it varies, right? Although I don't know C is, but I know that it's 1 minus C, 2 minus C, 3 minus C, and so on. So it's not a constant, so it's a variable. Then ask yourself, is this a random variable? For which, do you have the information about the probability associated to each of the value? So what's the chance that you got 1 minus C? So it's the same as getting a 1, right? So there's a probability associated to each value. So gain is a probability, is a random variable. So it makes sense to ask about what do we expect it, what is the expect value of gain? All right? So these are the values, and these are the values of the gain, and these are the corresponding probabilities. So to find the expected gain, so it will be x times f of x, and that means 1 minus c times 1 6 plus 2 minus c times 1 6 up to 6 minus c times 1 6. All right, so that is our, so it's 3.5. So in other words, you have to pay $3.5 to pay the gain. Then the expected gain is 0. That means you won't gain much and you won't lose in the long run. All right, so it's 0. It turns out that, maybe by coincidence, that this is just the average of 1, 2, 3, 4, 5, 6. All right? So it's happy. I don't know all this. Don't bother. I still get the answer 3.5. I just take the average of all this. Now, here's the problem. So suppose I tell you that the die is not balanced. So the chance of getting a 6 is only 1/10. And I adjust the rest. So that make up the sum equal to 0. And then ask you what is the expected gain. Oh, it's still 3.5. No. Okay, now let me ask a simple question. If I change the probability of having a 6 to, instead of 1 6, change it to 1/10. Then what do you expect about the gain? Would bigger than 3.5 or less than 3.5? Or equal to 3.5? What do you think? Of course, it will be less, right? Because the chance you got a 6 is less, right? So your gain will be smaller than what you gain here, 3.5. So you expect less, all right? I don't need you to calculate, but I just asked whether it's bigger than 3.5 or less than 3.5. So that's why you must know how to get the answer. How? It's not the answer itself. Take the average, you got 3.5 also. This is the gain, expected gain. But no, you get this answer because all the probabilities are equal, 1 6. But if I change the probability, instead of 1 6 for all of them, I change the getting a 6 is 1/10. Can I have the others are 1 6? Probably getting 1 is 1 6, 2 1 6, 3 1 6, 4 1 6, 5 1 6. Getting a 6, 1/10. Can I do that? No. So easy, right? Does not add up to 1. You must add 1 6. The last one must be 1 6 in order to get it to 1. Add 1/10 will not get it the sum equal to 1. All right? So yeah. Okay. Okay, so you have to pay $3.5 or units in order to get in the game, so that it's fair to both of you. Your other players and you. All right. Now here. All right. Okay. This is what I just did. I showed you. This is alternative way. All right. Okay. This approach is saying that, okay, what do you expect how much you will get? All right. So if you don't have to pay any money, you just play the game, then you will get $3.5 or units. So it's not fair. You don't pay anything, free lunch. I just pay the game. On the whole, I get $3.5. So now I want to charge you so that it's fair. Okay, I won't have to give you money. I also, will get money sometimes. So how much you pay is reasonable. So the answer is how much you get in the long run. So it's 3.5. So I ask you, each game you pay $3.5. So in the long run, sometimes you got 6, sometimes you got 1. All right. But then in the long run, we are even out. No gain for you and no gain for your partner. So that's another approach. This is to find out how much you gain, how much you get first. I shouldn't use the word gain. How much you get first, and then consider that money will be what you get. So you have to pay equivalent money in order to pay the game, so that it's fair to both of you. The second approach, that means the second approach in the notes, the one that I just mentioned, is to define a variable, y, which is I minus c. I is the outcome, and c is the money. All right, so I work out the expectation is 3.5 minus c. And in order this to be 0, c must equal to 3.5. All right? So this is what I mean by setting up the equation. This one, I want this to be 0, that means this to be 0. Solving this equation with unknown c, I got c equal to 3.5. So that is how it can be done. All right, another example. So, okay, this is similar. You want to insure this airline for 1 million. All right. So the insurance company calculate, all right, how much should I charge him? All right. So this is what actuarial will do, and actuarist will do. So estimate the chance. So here it says that, okay, a total loss will be 0.0002 chances. That means there's this chance that you will lose the lose 100%. And then 50% lose with a probability 0.001. And 25% lose with probability 0.01. And 10% with probability 0.01. So now, all these probabilities are probabilities. Does it add up to 1? No, right? Then what happens? Something wrong, right? What's wrong? So there's a large chunk, there's another probabilities referring to some event which is not mentioned here. So, although it's not mentioned here, but I think we have to assume that the last trunk referring to no lose, right? You buy car insurance, you buy accident insurance, you don't expect that accident will occur, right? With this probability. So there may be no accidents, all right? So the same apply, no loss, all right? Of course, you can argue that it can be, how about 60% loss? How about 75, no 75%, right? Or 73% loss? So we don't take that consideration. So basically, I try to break down the loss. It's from 0 to 1 million. I break it down into only 50%. Okay. In other words, the insurance company expect to pay out the total amount, 100% loss, all right, or 50%, all right, or 25%, or 10%. That's it, all right. So the corresponding probability are 0.0002, 0.001, 0.01, and 0.01. So they do not add up to 1. So there is a difference here, all right? But what's the value? So here, we make it easy, it's just no loss, 0, okay? All right? So we don't really consider whether it lost maybe $930,000. No, we don't. We ignore those. We just round it to how many percent. How about if I consider all possible values from 0 to 1 million? That becomes a continuous random variable. Then I may need a functional form to define how likely that I will lose at that amount of money. Let me repeat it again. Here, I use discrete, so I only take certain values. So that's why this 0 comes up. All right? So I explicitly state what are the probabilities corresponding to each of these values. So 100% loss is only 0.001 chance. 50% loss, that means I have to pay out the insurance company has to pay out 500,000. And the probability is 0.001. All right? And the rest of the value, except this 5, the chance of pay that amount is 0. All right? So it's considered discrete. So it's make life easier. But it can be, if you have able to construct, it can take the loss from 0 to 100 to 1 million. But the probability density should be in a closed formula, in functional form. What's a reasonable one? That is hard to judge. All right? So here we make life easy for us. So the point is that there's a value 0, no loss. All right? So as ignore all other partial losses. Okay? So that means that no other loss. So that means any values here, they are all considered no chance to occur. But this must be occur. So you don't have to pay out any money. So that is the rest of the probability. Now, the insurance company will not like to have a fair game. So that means you just pay the amount that it cover my expenses. I also want to make money. All right. So on top, I will charge you more. So suppose you work out what is the reasonable amount that this pilot had to pay. All right. But then you also the insurance company will charge an additional amount to make a profit. So that's what we are asked to do. So expected loss is 4,200. So this is a 0, and this is the probability of getting no loss. So the expected loss is 4,200. Okay? So in this, so far, the random variable is the loss. It takes certain values, in fact 5 values. And you have to figure out the 0. All right? It did not tell you there's a 0 there, but you have to understand that there's a 0 value, 0 loss. And then the corresponding probability, now I calculate the expected loss is 4,200. So if the pilot gave a premium of 4,200, it's supposed to be a fair, all right? But the insurance company does not make any money. So now it's charged additional 5,000. So it charged the premium 9,200, all right? So that's how it works. 5,000, about 100% profit, more than 100% profit of the cost. All right. Okay. So now we have this sales, gravel sales, X. So given by this PDF, is this bigger than 0? It's only bigger than 0 when this is true. When X is 1.5 or X is 2, then this is not positive. But we are limited to X between 0 and 1. And make sure that this one, when you integrate from 0 to 1 or from minus infinity to infinity, f of x dx is equal to 1. But if you are not asked to check, don't bother. All right, don't waste time. But if you're asked to check whether it's a valid PDF, then you better check. If not, assume that this is correct. Being positive is obvious, but checking whether this is true, you may have to do some computations. All right, what's the expectation of x? Now, I saw many times students just say, oh, expectation of x, integrate 3 over 2, 1 minus x squared dx. From minus, now this is wrong. Many mistakes here. First of all, this is f of x only valid for x between 0 and 1. Outside it, it is 0. So you have to partition the real line into 3 parts. From minus infinity to 0, and from 0 to 1, and then from 1 to infinity. You have to add these 3 integrations. But this part and this part will give you 0 because the integrand is 0. The PDF is 0. But again, there's another mistake. We are asked to find the expectation of x. All right? Even if you do it correctly, okay, not from minus, still to 1. Okay, I know the answer. 1. The answer is 1. What's wrong? You are asked to find the expectation of x, which is not integrate the f of x. It's integrate x times f of x. Don't forget about this x, all right? X times f of x. All right? So that is the expectation of x. Hey, how about expectation of x squared? So it's the same thing. You just have to replace. For continuous of discrete, it's the same thing. For continuous, it's integrate from minus infinity to infinity, x squared times f of x dx. Or summation x squared f of x dx. All right? Over all possible x values. How about x cubed? I replace this by x cubed. Okay? How about sine x? Replace this by sine x. All right? So, in general, any function of the random variable x, if I want to know the expectation of it, is equal to integrate or summation, all right, that the function gx times the PDF of probability function. Okay, it's like that. That means whatever you try to find the expectation, which is a function of a random variable, what you do is just this function of the random variable times the corresponding probability function or probability density function. If continuous, you do the integration. If it's discrete, you do the summation. All right? Okay, so this one you can get. So you do the integration. It's just a polynomial, easy to get. So the expectation is 3x. 3x. All right? So, this is another example. This one, they divide this x, the range of x, for which you have a different form of PDF. Basically, there are 4 regions, from minus infinity to 0, from 0 to 1, and from 1 to 2, and then from 2 to infinity. There are 4 different integration. To break it down from integrate from minus infinity to positive infinity, there are 4 integrations. All right, but within minus infinity to 0, the PDF is 0. Within 0 to 1, the PDF is x. Within the x between 1 and 2, the PDF is 2 minus x, and this is 0. All right. So if I proceed to do the integration, what is the answer? So these are the f of x, then dx, right? dx, dx, dx. So what's the answer for this one? 1. This is the PDF, integrate from minus infinity to infinity f of x dx. You do spend a few minutes to integrate it. I tell you within 2 seconds the answer is 1. All right. Okay, but that's not what we want. What we want is the expectation of x. All right. The average number. So that means the expectation. So you have to multiply x, multiply x, multiply x, and multiply x. All right. So you need to do something. You need to do the integration. All right? Hey, by the way, how do I know that this is positive? Yes, of course. X is less than 2, so this is always a positive number, greater or equal to 0. All right, so do the integration. So you see, instead of 4 integration, I only have to do 2 integration. So straightforward computation and get the answer. Ooh, turn out to be 1. It's just by coincidence now, this one. All right. It's just by coincidence the expectation of x equal to 1. All right. Okay. So, that's another point. This is 1. It's 1 unit corresponding to the expression of the PDF. But when you interpret the results, you have to go back to the question. 1 means 100 hours. 1 unit in the whole question means 100 hours. All right, so you have to. So in fact, the way that we define the PDF, it means, based on this one, it means that the machine only works at most 200 hours. After that, it will not work. So this is not a very good example or good form to represent the period of this vacuum cleaner works. Usually for this kind of thing, it is just like a life of a machine. All right. So a life better represented by a function like this, exponential function. So what we have here, this function is look like this, up from 0 to 2. All right. But a better way to represent it is like an exponential function. Although you don't expect the vacuum cleaner will work for 10 years, 100 years, a million years, right? But that's how usually we represent it. All right. This is not a very reasonable one. So we after 200 hours, it will not work. All right. Okay. So expectation of function of random variable, I just mentioned it. So it just replace it, x by gx. All right. For continuous, integrate. Very simple. All right. Here's special case. This one, when you take expectation of this, we have a name for it. It's called variance. So that's the definition. Now, so what does it mean? It means that we are talking about the x, how far what's the difference between x and its center or its expected value? X minus mu x. That's the difference between your value x and what you expect. All right? And then the difference, we take a square. We square it. Now square have 2 functions, I may have two characteristics here that I would like to mention here. First of all, when you square it, then it doesn't matter whether x is bigger than mu x or x is less than mu x. That means we try to get rid of the sign. We don't bother whether it's, so long as it's far away from the center, then it doesn't matter whether it's bigger than mu x or less than mu x. So that is one why we square. The other reasons why we consider square is that, all right, if you are not too far away, okay, we will take it. But if it's very far away, we try to make the impact greater or larger. So that's why we square it. So for example, if the mean is 5, all right, if you have 10, so the difference is 5, all right. But if I square it, so now the square is 10 minus 5 becomes a square of 10 minus 5 will be 25. So suddenly your difference, your square of the difference will explode. So what I'm trying to say is that if the mean, for example, is equal to 5, we look at x, takes the value 10. All right? So the difference between these two numbers is 5, mu x minus mu. All right? Now, how about consider x equal to 9. So x equal to 9, then x minus mu is equal to 4. So 4 and 5 are not much different. But let's consider the square. Square of it this is 25. Square of the difference, this is x minus mu square. So x minus mu square is 16. 16 and 25 is quite big difference, right? It's almost only 2/3 of the original one. All right? So it enhances the difference. If the difference is big, it's even bigger. All right, you square it. So variance or expectation of the square of the difference of x minus mu is to measure how the data, how the distribution are varied. So in other words, if you see something like this, let's consider. So this is the center. So a lot of the observations are near to the center. So in this case, the variance will not be too big. But if you have a distribution like this, all right, then this one means that there are a lot of chance that, not small chance that you will get value very far away from the center. So in that case, the variance will be big. All right? So I think I have to stop here and continue on Thursday. All right? Okay, so remember we have this midterm test week 7, I think it's 5th of October, Saturday morning.